today on Console. This is Robin Elgart, space radiation element scientist. She will discuss the deep space radiation environment and what we are learning on missions like Artemis 1. Hi, Robin. Thank you for joining me today.
Thanks so much, Shaniqua. I'm happy to be here.
And can you tell everyone what a space radiation element scientist is?
Of course. So as a space radiation element scientist for the Human Research Program at NASA, I am responsible, along with my excellent team, for developing and executing a robust research strategy to understand, characterize, and hopefully mitigate the health impacts to humans from the space radiation environment. And so when we talk about space radiation, why does NASA care? Well, turns out space is a radiation environment, and so our astronauts are actually radiation workers. And so that means that we know that radiation is a health hazard for them, and we need to do our best to characterize that and mitigate that. And so this radiation comes from 3 different places in our universe. First, we have our galactic cosmic rays. Galactic cosmic rays are theorized to be the result of stellar explosions, where things like supernova are accelerating particles throughout the universe. Right? And so you can imagine how fast these particles are going. And then we have trapped radiation. Trapped radiation is actually a consequence of our Earth having a beautiful magnetic field, and it protects us from all sorts of things, but it also traps some of that radiation that's zipping around out in our solar system inside these belts, which are called the Van Allen belts. So those are these sort of donut-shaped rings around our planet. And then thirdly, and probably the most well-known, are solar particle events. And these are when the sun sort of belches out some extra solar particles and out into our solar system.
Okay, and you mentioned solar particles. Can you explain a little bit of what those are and how they could affect the Artemis missions to come?
Absolutely. So the sun is a giant rotating ball of magnetized plasma, which is sort of mind-blowing when you think about it. And it creates an incredibly complex magnetic field throughout our solar system, and also on what we think of as the surface of the sun. And those some localized areas of the sun those magnetic fields in those localized areas can get really tangled up and entangled with each other, and that creates something that we all know of called sunspots. And you can actually see these with the appropriate kind of telescope from down here on Earth. These sunspots can create sort of active regions where the local magnetic fields are really entangled. And just like anything, you can, something that builds and builds and builds energy, at one point it just gives up. And so these magnetic fields, they break and they reconnect down into a lower energy state. That energy has to go somewhere. And so that energy is released at this huge amount of energy release, some of which can actually push particles out from the solar corona, as well as the particles out in the solar system, out into the solar system. And so that's what's called a solar particle event, when those particles are accelerated out from the sun out into the solar system.
Awesome, and that is definitely something worth caring for. On Artemis 1, on flight day 13, on November 28th, Orion reached its maximum distance from Earth. Now, we know that that maximum distance was 268,563 miles from our home planet. How will being further from Earth affect our crew on future Artemis missions?
That's a great question. So because those Van Allen belts that surround Earth and protect us from things, beyond those, the crew will no longer have protection from galactic cosmic rays, those particles that are accelerated because of supernova, or those solar particle events. So if there's a solar particle event headed your direction and you're outside the Van Allen belts, you have no protection from our beautiful, snuggly Van Allen belts anymore, right? And so them being further away from Earth means that in mission, real-time monitoring of the solar environment is really important, because if you are going to be exposed to these solar events, we have to have some way to shield it, because even though we can't shield from galactic cosmic rays, we can shield from solar particle events relatively effectively, and it doesn't take much. So our operational team, the Space Radiation Analysis Group, or SRAG, they've actually developed an awesome protocol, which is to build a storm shelter. And I think we have a great video that demonstrates what this looks like.
My name is Jessica Voss, and this is Anne McLean, and we are here today helping the designers of the Orion capsule evaluate the ability to protect their crew from radiation. Radiation, as you know, is really harmful, and so the whole point is for us to get into a really cool little shelter and take all the equipment we have in this capsule and put it over us as best as possible. And we have to make sure it's stowed and that we are safe and we have everything we need in terms of supplies down in this awesome little bay.
So you can see there, they build this basically is what amounts to a pillow fort, and putting all of that mass around them to keep those lower energy particles from solar particle events out of their little pillow fort there, and keep them sheltered from that storm.
And you're saying pillow fort, but the pillow fort is stowage bags and different things that are already in Orion for the crew, and they're using that during a solar particle event to protect themselves.
That's exactly right. And so they can hang out in that little area for the entirety of the event. Of course, they can come in and out of that shelter. They don't need to stand there the whole time, but we want them to spend as much time as they feasibly can inside that shelter. And right, it's just using stuff that we already have on board to sort of even out that mass distribution.
Gotcha. And so as far as protection goes, again, for our astronauts on future missions, we know this is an uncrewed mission, but future missions will have astronauts aboard. What can we expect beyond this for astronaut protection in terms of radiation?
Great question. So like you said, this is, it's uncrewed, but even on these first short-term missions, we are still learning things about the radiation environment. We have a radiation detector up there now, HERA, which is constantly taking data right now, and we're actually seeing how what makes that pillow fort. We have a sensor in there right now, and we can see that it actually is providing protection compared to the sensor that is outside of that bay when they transited through the Van Allen belts, because it's a similar type of radiation to solar particle events. But moving forward, the uniqueness of the space radiation environment really makes for a hefty challenge when it comes to doing research down here on the ground. So we don't have the same amount of protection strategies up in space as we do down here on the ground. Usually when you're in a radiation oncology department, you have time, distance, and shielding. Well, in space, you can't get away from the solar radiation and the galactic cosmic rays, and you can't really shield it either. So the only thing we have is time. But of course, if we're talking about a year mission to the moon, we're talking about 3 years mission to Mars, time starts to become a problem too. So that's where the space radiation element is coming up with new strategies of how we might be able to protect the crew, which includes things like health monitoring, early disease screening for the things that we are concerned about, including cancer, cardiovascular disease, immune changes, and potentially even neurocognitive defects, as well as looking for some sort of compound-based countermeasure that can help the body protect itself from that biological damage. We might not be able to stop the physics, but we might be able to help the biology.
That's amazing. I know our crew will need to be protected from those rays as we enter into future Artemis missions. On our future missions, we talked about the protection, we talked about space radiation. Is there anything left that we didn't talk about that would be relevant to what we're learning about space radiation on this mission or even future missions that are planned?
On this mission in particular, I really just want to give a huge shout out to our operational team, the Space Radiation Analysis Group, because they've worked so hard on getting their detectors up to speed, and they're really starting to see their models play out. They saw when Orion went behind the moon and came back out, and we finally got that signal again. Sure enough, there was a 30% drop because of the moon itself providing shielding to the capsule. And so just a really huge shout out to that team, because they have done done an amazing work. They're working 24-hour console to support this mission, and they really deserve mad props.
Thank you very much, and thank you, Robin, for coming and joining us here today, telling us a little bit about the deep space radiation environment and why it's important to the Artemis missions overall.
Thank you so much, Shaniqua. Happy to be here.
Thank you.